All right, finally, we've got combustion analysis. This is generally used for hydrocarbons, but you can use it for pretty much anything. Right, our hydrocarbons are things that contain hydrogen and carbon, and pretty much that only. So we've got CXHY. We don't know how many of each they contain. And as the name implies, the first thing you do is you combust your products or you burn them. And then after that, you're going to weigh the products. If we think about a hydrocarbon, what's our products of combustion going to be? Well, they're going to be carbon dioxide and water. And so you have some kind of setup like this taken from your textbook. You have your sample in here. You pass through a bunch of excess oxygen. You burn your sample. And then you've got some kind of water absorber, which will absorb any water that your product forms. And then a CO2 absorber that will absorb any CO2 that you get. And so that way you'll be able to tell how much water and carbon dioxide you formed. And then if we think about the chemical reaction here, we have our CXHY plus our O2. And that's going to form H2O, CO2 plus H2O. Well, if we think about where all the carbon from our carbon dioxide is coming from, it's coming from this CX, right? So however many carbons are on the left side have to be on the right side, and so our X value here will be the same, right? However many carbons we had, if we had 5 carbons, we would have 5 molecules of CO2, and so on and so forth. If we think about where all of our hydrogen is coming from, well, it's coming from our hydrocarbon as well. And if you think about the stoichiometric ratios, we have 2 hydrogens in this water molecule. So for however many hydrogens there are here, we'll get half as many water molecules, right? So this would be kind of Y over 2. Because for every 1 hydrogen, you only get half a water molecule, or you need 2 hydrogens on the left side to make 1 water on the right side. Let's take a look at a potential example, a 0.00256 gram sample of hydrocarbon is burned and produces 0.00788 grams of carbon dioxide and 0.00322 grams of water. What is the empirical formula? Right, so in this case, we're asked for the empirical formula. How many carbons, how many hydrogens, what's the ratio there? So we did these types of questions previously, so we're going to use similar techniques. So let's focus on the carbon first. We know this is how much CO2 we form, 0.00788 grams of CO2. We, of course, want to go to moles of A first, so we'll divide by 44.01 grams per mole. And then we want to get to moles of carbon. And we know from our equation for every 1 CO2, it must have come from 1 carbon. And in this case, we want to stop at moles because we want to find an empirical formula. And so you should get about 1.79 times 10 to the negative 4 moles of carbon. And then we'll repeat the same process for hydrogen. So we had 0.00322 grams of water. Of course, we want to convert that to moles. And then use our stoichiometric relationship, right? We know for every 1 water molecule, there's 2 hydrogens from the original compound. And then we want to stop at moles because we want an empirical formula. All right, so there's how many moles of carbons and hydrogens were from our sample, and then we just follow the steps from our kind of section of how to discover empirical formulas. We write the empirical formula with all these numbers, 1.79 times 10 to the negative 4, and then hydrogen, 3.57 times 10 to the negative 4. Divide both sides by the smaller number, which is 1.79 times 10 to the negative 4, and then we get CH2, right? That's our empirical formula. If you wanted the molecular formula, we'd need to be given more information about this. We need to be given its molar mass, right? So we can't know the molecular formula without additional information. Note that if you look at a question, we didn't use all of our pieces of data. We didn't use the mass of the original sample. So that's something that we didn't use. And that's something that we didn't use in this example, but you may have to use it in the future. So what would you need to use the original sample mass for? Well, that's if the question asks for maybe something like mass percent. Right, if we wanted mass percent, then we'd want our mass of our component over the mass of the sample. So for example, if we wanted to calculate the mass percent of carbon, we would then take our moles of carbon, and then we'd keep going, right? We'd convert that to grams. Mole here. End up with 0.00215 grams of carbon. That's our mass of X, and then we just divide by the total mass of our sample. Multiply by 100% because it's a mass percent. And you get that it's 84.0% carbon. And then you could do the same thing with hydrogen. So you're not always necessarily asked for the empirical formula. That's one of the more common questions, but you could be asked other types of questions for your combustion analysis. For example, if it wasn't a hydrocarbon, but it still contained some amount of hydrocarbon, you could figure out the mass percent of carbon and hydrogen in each, that kind of thing. Depends what the question is asking for. Depends what you want to do in these kind of real life scenarios.